Welcome to this video. In this video I would like to talk about forces on particles and the special case of particle motion in 2 dimensions. So if we take a look, you learn what changes for particle motion in 2 dimensions, because in the previous videos we looked at how a particle settles or rises, and therefore we just looked at 1 dimension, and now we would like to extend this to 2 dimensions. And therefore we define the force balance for motion in these 2 dimensions. So again, we will use a force balance. And then you will learn how a Python code can be used or written to solve this problem and calculate the trajectory, so the path the particle moves in 2 dimensions. So that's the idea of this video. And if we take a look, so for particles in 2 dimensions, so the example I have here is a droplet, because in the corona time we had this 1.50 meter distance because of the flying of droplets when I sneeze or cough, right? And so what you can think of is this is a particle, it's a droplet out of my mouth when I sneeze. So, and this means when I sneeze, the particle will go like this, but also falls down. So we have a 2-dimensional motion. So we have the y direction, the falling down, the settling, but we also have a velocity in this direction, right? Because the droplet comes out with a velocity, and therefore this is a very classical and also good example for moving in 2 dimensions. And to describe this, we again make use of a force balance. So we have to take a look at the forces acting, and first of all, as I mentioned, the velocity, so that the particle starts with the velocity, and when it comes out, the velocity is straight, and then the gravity pulls the particle down, right? So the first force we have to consider is gravity force. And as you know from the previous videos, gravity is mass times g, and the mass can be described by pi divided 6, diameter cube, density of the particle g. And important to notice is that the gravity only acts in y direction. Okay, so the gravity does not have a component in x direction, because gravity only acts downwards. And then we have the buoyancy force, right? The buoyancy force is the counter force to the to the gravity force, and therefore the equation is the same. The only difference is the density of the fluid and not the density of the particle. And similar like gravity, buoyancy acts only in y direction because it's the counter force to the gravity. However, once the particle leaves my mouth, it just has a x component, because I sneeze, in a very easy case, I sneeze straight, but since the gravity acts, the gravity pulls down, so the starting velocity is only in x direction, but when the gravity starts to pull, the velocity changes, and now it goes in x and y direction, right? It doesn't stop and fall automatically down, but it stops to just go in x direction. It falls down due to the gravity. And again, the motion of the particle, we have, of course, the drag force, right? And the drag force here is calculated in Stokes' regime. So a simplified version, we have a previous video where we explain in more detail how this drag force works and why the Stokes equation looks like this and what is the meaning of the Stokes equation. And the drag force is the counter force to the moving velocity, right? Very simple equation, velocity, diameter, and this force now has a y and x component, right? It goes into both directions. So to understand this, we have to, we directly start with the Python code. So now the problem we have is that differently to settling in 1 dimension, where we very easy can calculate the final velocity or the settling velocity, the terminal settling velocity of a droplet or a sand particle or whatever. Now it's more complicated, because now we have to calculate in x and y direction, and then we have to put everything together, and so solving this system is more complicated. And this is something you need to do with the computer. It's really hard to do this with pen and paper. And therefore, I suggest to do it with Python, because in my class we work with Python. Python is open source. And the first thing you need to do is to import libraries, and we use two libraries, NumPy and matplotlib. And the NumPy is what we need for math operation and arrays, right? If the math we are doing, the arrays we're setting, where we put values in, therefore we need NumPy, and I want to have a nice diagram at the end, and therefore I need matplotlib. So we're importing these libraries that my Python has the function in these libraries. So without matplotlib, my code cannot plot a diagram. He needs this library to do this. Then we set some physical numbers, right? We tell the computer G is 9.81 meter per square second, so it's an acceleration. The density of water is 1000 kilogram per cubic meter. The density of air is 1.225. You also can calculate with 1 at the end. It's not that important. The viscosity of air is 1.8 10 to the power minus 5 Pascal seconds, so 18 millipascal. And these are the numbers we need. So then we also need some data for the droplet. And the data for the droplet is, I want to calculate 3 droplets to see some difference. So I assume that I have 3 droplets, and here all have the same size, 200 micrometers, but each of them has a different starting velocity. So this is the diameter, 200 micrometers, so 10 to the power minus 6 meter. And the velocity is 10 meter per second, 15 meter per second, or 5 meter per second. So here in this array, I can play with the size of the droplets and the velocity of the droplets. So I can change this and then calculate, or ask the computer again to calculate. So here are some settings which I just need to start my calculations. And then I have some more, and this is the colors for the plot. I could do this later, but I already have it here. So colors for the plot, it's mean when I get my diagram, I have blue, sky blue, dark blue, and I have labels here, which get some names later. It's empty so far. And then we need some time steps, because the computer is, so the droplet comes out and the computer is calculating the velocity and the position for a certain time step. So if I give the time step 1 second, I sneeze, and after 1 second I get my information. That's not really good for me. So I define a quite small time step, right? So 10 to the power minus 3 seconds, so that I get a time step here, 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 and then I see the path of the droplet. And I give a maximum time. So the maximum time is 5 seconds. And for the simulation, I need the time from 5 to 25 seconds, because smaller droplets than the one you saw before need more time, right? And it could be that, so we have here a finishing criteria, which means after 5 seconds, so the simulation goes for time, and after 5 seconds it stops, it's finished. Okay, so we have a criteria to end the simulation here, and we put all of this in one variable, which is t_vals, and here we have 0 seconds, 5 seconds, and the steps in between from 0 to 5. Okay, so now I also include an angle, and the angle is 0 at the moment, but what also could be is that if I sneeze upwards, my angle is 45 degree, 20 degree, or if I sneeze downwards, my angle is in downwards direction. And especially because this calculation can be used for any particle moving in 2 dimensions, so it's important to have this starting angle considered. But we go from a straight motion, and therefore we say starting angle is 0. And here we go from radians to degree. It's just to calculate with degrees. Okay. Then we have preparing the plot. So here's already the size of the plot. You can do it also later, but at the end it doesn't matter. And here now we have a loop, and this is a loop over each droplet. Okay, so here we start the loop, and here you see Tropfendaten, which is the data for the droplet. I have here, right? So these are the 3 droplets, and the loop goes over each droplet. And the question is, what is the loop doing? And the loop, first of all, needs the droplet size, while droplet size we already have, so maybe it's a little bit, but here the informations of the droplet I need in my equations. And in the code I do it with radius, you could do it with the diameter, doesn't matter, at the end you just have to be consistent. So the radius is half of the diameter, the droplet size in the beginning is given in diameter, so here we have the volume of the droplet as a function of the radius, the area, cross-sectional area of the droplet, and the mass of the droplet. So here we have the droplet informations, which we need when we calculate the acting forces. And here we have now the force balance. So we have gravity, right? We have buoyancy, and and we have drag. And from drag we use something called friction coefficient or friction constant. And the friction constant is this K. And K is 6 pi viscosity times radius. So what is missing here is the size and the the size is in the radius, the velocity is missing, right? So basically that's the drag force without velocity. So in the previous slide, the drag force was 3 pi viscosity, diameter, velocity, and now we calculate in radius, so it's 6 pi viscosity, radius without velocity. And then we have something called a time constant, and this time constant is the mass of the droplet, which we calculate here, divided by K. Okay, and this is the ratio of the mass and the friction. And if we look at the units, the friction constant has a unit of kilogram per seconds. Okay, so we have here Pascal seconds, and here we have meter, and this gives kilogram per seconds as a unit. And if we have the mass, which is kilogram, divided by kilogram per seconds, this gives a time, right? So mass, kilogram, divided by kilogram, divided by second, kilogram goes out. 1 divided by 1 divided by second is second, so this is a time constant. And we will need these constants because here we have a so-called final velocity in y direction. So the final velocity in y direction is what we calculated in the previous videos as the final or terminal settling velocity. So the falling of the droplet can be separated in x and y direction, and in y direction the droplet is accelerated by gravity. And this means the droplet will have a final velocity, right, with which it's falling down. It's not going to infinity once it reached its final velocity, and that's the velocity we calculated in the previous videos as settling velocity or terminal settling velocity. And this is basically buoyancy minus gravity, right? So the buoyancy minus gravity, the gravity accelerates downwards, the buoyancy again, and then we also have the drag force. And if I want to have a velocity, I have the drag force equals the buoyancy minus gravity. You can see this from the previous video. And now I just leave the velocity on the left part and I put everything else from the drag force, and this is the friction constant, right? This is all in here times velocity. And if I put all of this, I just give this the name K and put it on the other side, and then I can calculate the final velocity. So the final velocity is the buoyancy minus gravity divided by the friction constant. And this is why we define the friction constant here. Okay, so now we have the forces, we have friction coefficient, we have a time constant, friction constant, we have a time constant, we have a starting velocity, and so on. And now we have to consider another thing, and this is very basic math, and this is x and y direction, and g only goes in y minus y, b only goes in y plus y, but d is a force which has two components. And to calculate these two components, we need cosinus and sinus. First of all, we need this angle here, alpha, which is here. We have the horizontal, so it's the angle between the force arrow and the horizontal, or here the velocity and the horizontal, so the angle here. And if we have the force, we have a x component, so in x direction, in this direction, a certain part of this force acts, and this is F multiplied by cosinus alpha. Okay, this is the part of F acting in this direction, and we have a part of this force acting in y direction, and this is, sorry here for the error, F sinus alpha. So I'm very sorry for this, but we have sinus alpha, not cosinus alpha, it's a typo. So F sinus alpha, F cosinus alpha. In x direction, F cosinus, in y direction, F sinus, if the angle is between F and x. And if we consider this, we can now, the same counts for everything, right? And also the velocity has an angle here. So also the velocity has a y direction and a x direction. So this means we have to consider this, and this is the starting velocity in x direction, starting velocity in y direction, and this is the starting velocity multiplied by the cosinus of the angle. So I said that the droplet goes straight out, horizontal, right? So the angle is 0. And this means we have the starting velocity multiplied by cosinus 0, and this is 1. So the full velocity goes in x. And this makes sense because it goes only straight, right? Only horizontal. And now we have the y component, and the y component goes with sinus of the angle, and the angle is 0, so sinus is 0, so there is no y component. So for the first time step, the droplet only has x component, so it only goes horizontal and doesn't has any component down. But then the gravity starts to act and changes the direction, so we get an angle, and with the angle we get a decreasing x and an increasing y velocity. So that's already a lot, but we are not done with the loop. So what we have here is now an analytical solution of the velocity of time. So we have an x velocity and a y velocity, and the x velocity is basically decreasing with time, and that's the function. So here we need the time constant tau, and the larger the mass, the larger this time constant, and this means the slower this function decreases. So this is an exponential decay, so this means the velocity in x direction exponentially decreases, right? So here's the variable, and this means we have an exponential decay over time with a constant here, and the larger this constant, the slower the decay, and this means that a small drop or a fast droplet decays very fast, and a large droplet decays slow, and a small droplet decays fast. Okay. So, and here we have the same in y direction, but in y direction we already have a final value which we reach, right? Because in x direction we have a decrease of the velocity, and in y direction we have an acceleration, so an increase of the velocity due to the gravity. So in x direction the drag decreases the velocity of the droplet, and in y direction the gravity increases the velocity till we have a final velocity, and at the very first this part here is this part here equals this part, and with increasing, so we have a minus, right here minus, and with increasing time this part gets smaller, 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 so this part gets larger, 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 and it converges to y in y, so till the infinitive velocity. Okay, and then we now calculate the position of the droplet. So if we have the velocity of the droplet at each time step, we can calculate by a numerical integration, right? Numerical integration of the velocity gives the position in x and y direction. So this is done by the computer, right? NP cum sum. And this gives basically the x and y values for the position. So here, here, here. So one thing is the velocity at this point, the velocity at this point, and the other thing is where is the position, right? So, and then we have a second cutoff, and this is if I'm saying, okay, the droplet comes out, but I have a finite size, so 1 meter 80, 1 meter 90, and I said, okay, if you simulate, rather after 5 seconds the simulation is done, or if the droplet has fallen 1 meter 80. So if I assume a person in the size of 1 meter 80, here is a cutoff criteria that once the droplet reaches the ground, we don't need to simulate anymore, and the loop stops. Then we have here plotting the trajectory. So we have all the positions which we calculated and collect. And now I want to see the diagram of these positions, and this is what we have here. And then I also have the final value, which is saved after 1 meter 80. So I want to know what is the final distance the droplet traveled. Here's some formatting of the diagram, right? That the diagram looks nice. And at the end, the code also gives me the distance with a height of 1 meter 80. Then I have the final value. And to sum up, I think this was a lot in detail, right? But I really would like to go down part by part through the code. And what you see here is what the code is generally doing. So we compute physical properties, we compute the radius, the volume, the mass of the droplet. Then we put the forces in there, the gravity, the buoyancy. We have the air drag coefficient, which comes from the drag force, but it's a short way because we want to have the velocity. Then we determine the motion parameter, therefore we need the time constant tau and the terminal velocity, which is the final velocity in y direction. We set the initial velocity, horizontal and vertical components. So the vertical component is 0 at the beginning, and all the velocity goes into the horizontal component. And then we solve the velocity over time using an exponential decay. This is Stokes' drag law, right? So you will see it decays exponentially, which you also see in the equation. And then we integrate the velocity to get the position in x and y. We stop the simulation when the droplet has reached a height of 1 meter 80. And then we want to see the trajectory of the positions from the start until the cutoff point. And finally, we also record the flight distance, so the final distance, which is printed by the code. So if we take a look now, this is the result. So we have 3 droplets, 200 micrometer, 200 micrometer, 200 micrometer. This is the 1 meter 80 high. So this is my mouth. And then the droplet starts. And now you see the faster the velocity, right? Starting velocity, the further the droplet goes. And you really nicely see the exponential decay, which is in this case quite large because the droplet is quite large. And you see the distance the droplet can travel, and here you see less than a meter, a little bit more than a meter, and 1.75. So you get a little bit an idea why 1 meter 50, right? This is a purely mechanical calculation of the droplet path, and we see that if I sneeze, how the droplet will fly under certain velocities. And if I now look at the different sizes and fixed velocity, so I take a very fast, and this is the velocity I can get for sneezing, and then you can see that large droplets with 25 meter per second can go up to 3 meters even. And you see with decreasing size, the exponential decay goes very sharp, right? So this is due to what I said, the mass divided by k, so tau. That's the explanation why the exponential decay is so fast for small droplets. And you have to be a little bit careful because we only balance 3 forces here, right? But in reality, for small droplets, also some other effects come into play. So based on this model, a small droplet of 50 micrometer only goes 25 centimeter, but the settling time of this droplet is already very large, and there are some other effects moving the droplet, so and they are not considered in this model. So this model gives a very nice, very simple picture, right, how to describe this trajectory, but we can learn already a lot, and we can really calculate the traveling distance of a particle in 2 dimensions. So I have some tasks for you to train your knowledge, and this is that you set up the force balance for your own. Okay, take a piece of paper and just make the force balance for your own. And also rethink that, because we have drag force, we have buoyancy, and we have gravity. And then also with the other videos, you can recap why we define this friction constant and why we take a part out of the drag force K, and then we have the velocity, and why this is important for the code. And with this, you can write the Python code for yourself and plot the diagrams. All the code is in here. You can do it with the video, but do it for yourself to understand what the code is doing and how and what happens when you play around with it. And then think, and that's really advanced, think about a numerical solution for the force balance you set up here on your own in X and Y direction. So don't ask the computer to solve it by your own. And this is already advanced, but it's a very, very good training. So with this, I'm done with the video. I'm sorry, it's quite long video and we have some complicated part here. I think what changes for particles in motion in 2 dimension is quite easy, and the force balance also is quite easy. But then when we start to separate in X and Y direction, it gets a little bit more complicated, and I hope it wasn't too complicated in the explanation when we try to translate it into the Python code. But I hope with this you learned how to make the force balance in 2 dimension, how to use a Python code to solve the problem, and how to plot the trajectories. And with this, I'm finished with this video, and would like to thank you for watching.